You can kill the session.
Okay.
Always.
Yeah. So we've already gotten our talk title lovely introduced, and I'll just say that Han and I are going to be presenting this talk, and it's joint work with Aaron Roth, my wonderful advisor. Okay, so for those of you who were here just a few seconds ago, I just want to briefly, this problem is, it's different, but like there's some connection. So I wanted you to keep my two important differences, which is we still have sort of a leader-follower problem. They're now called principal and agent, but now the principal does get to see the agent's utility. But we're also making this a different and harder problem in a different way, which is there's an additional sequence of states of nature that the principal and agent's utilities depend on. Okay, so we're in a repeated principal agent setting, and we're in a setting where, in the standard assumptions are in this setting, is that you can have a principal and agent who both have some shared prior over some state of nature. And so this is how the standard model works, which is in each round, you'll have the principal who commits to some policy. The agent's going to best respond with some action. The principal's utility is some function of their policy, of the agent's action, and of the state of nature. The agent's utility is also a function of these things. Okie dokie. So just looking at a brief example of this, in the repeated contracting setting, you can imagine that the principal's action each round is a mapping from rewards. So you can see, in this example, maybe the state of nature is whether a task is hard or medium or easy. Our agent can decide to work or shirk, and there's some cost for both of them. Presumably, it's harder to actually put in the effort. So the principal is going to then receive, there's going to be some reward depending on whether it's hard, medium, easy, whether there's a work or a shirk, and they're going to map that to some payment to the agent. And the agent, seeing this, is going to decide what they're going to do. Principal's utility is their reward minus their payment. The agent's utility is their payment minus the cost of their action. Okay, so, and in the standard assumption here again, the principal and the agent might have some agreement. They both have a shared prior over how likely they think the task is to be hard or medium or easy to complete. But we are interested in removing this assumption of a shared prior, right? It might not be that in these sort of repeated principal agent settings, the principal and the agent both have exact agreement over what they think the distribution is, or that they're right? These are both assumptions that are implicit in the previous model. Okay, so now, what is the principal going to commit to, right? They no longer have a prior, but maybe they still have a forecast. So in this work, we're going to think about what you can do with a calibrated forecast, even if you don't have a prior. Okay, so the principals now, instead of committing to an algorithm that's mapping from histories of play to policies at each round, they're going to commit to a choice rule that's mapping forecasts at each round to policies. Okay, so let's take a look at what the principal-agent interaction is here. So now at each round T, the principal is going to obtain some forecast, pi T. So there's some external forecaster, and we're going to see these are calibrated, but like for the model itself, right? Like it can be whatever, right? And they're going to commit to a policy, PT, right, which is derived from a mapping from this forecast, determined by their choice rule. And they're going to send that to the agent. And additionally, they will also send a recommendation of what the agent should do. And in particular, this recommendation will be the thing that if this forecast was actually the prior, then it would be the best response given this policy they're committing to. So they're sending both of these pieces of information to the agent. And knowing this, the agent will respond. I'm not going to tell you right now how they're going to respond. We'll talk about it more later, but they'll come up with some response. And then the state of nature is revealed to both the principal and the agent, which will then at this point determine their utilities for that round. Okay, so what's our goal? We're going to try to minimize policy regret in this setting. So let's talk about our benchmark. However we did for the actual choice rule we chose, when we look at the benchmark, we're going to say the forecasts are the same and the state of nature sequence is the same, right? So we didn't create this forecast. We're using a forecast. But now we're going to say we're committing to the best constant policy, which means every round I'm picking the same, policy in my action space to commit to. So that's different. The recommendation now is also different because it's, dependent on the policy. And now the agent, again, I haven't totally defined what their behavior is, but like we'll also let them now respond different, right? Okay, so this is the policy regret benchmark. So what's the utility in every round? This utility of the principal is like, so here we have the principal with their little policies. Then, there's some state of nature, and then the agent has some actions, right? So like that's what you actually get. And then we can think about, right, counterfactual, where you just play one fixed thing. State of nature is the same, but the agent can change their actions, right? And we want to see how well we do in comparison to this, the best choice of this fixed action. And the adversary, right, this state of nature sequence is going to be chosen to try to maximize this gap. Okay, so now I know you're all very excited and waiting for it. We're going to talk about what the heck what it means to think about what our agent should do now, right? So we no longer are able to make these nice, tight, best response assumptions that made in the paper with Ishwar and John. We have to try to generalize this best response rationality to a prior free setting. Okay, so here's how we think about the important key things. We're going to try to say that all the assumptions we're going to make like also hold in the setting with a prior, so it's a strict generalization. So in the standard setting, we have a shared prior, right? And what does that mean? It means that they both kind of have the same amount of information, right? They both agree on this prior, but they also don't know anything more than the prior, right? So they know the prior, but they don't know, they can't actually guess what the true draw will be, right? In our setting, we generalize this with an assumption that we call no secret information. Okay, so no secret information means that if we condition on the principal's choice of policy, recommendation, right? The agent's action is independent of nature. So the agent doesn't have some more extra secret information that the principal doesn't have, that they're using to sort of exploit the situation, right? So we see here, like, okay, like there's no pattern we're seeing here. Okay, the second key thing that happens in the standard setting is that not only is there this shared prior, but the agent's gonna best respond to it every round. So we still want some notion of, being rational, being strategic for our agent. So we're going to say that they have no contextual swap regret. So this is also a strict generalization. So what does this mean? We are again going to condition on the principal choice of policy recommendation. And under this, we're saying the agent has no swap regret, right? So keeping the state of nature fixed, we're going to say that if the agent, swap their actions, they're not going to improve. This is certainly achieved in the prior setting because they're going to be pointwise optimal every round. And so this is just a generalization of that. Okay, so, oh, I was going the wrong way. Oh, wow, I went really far. Okay, finally, typically in these settings, we think about the agent being able to tie break in favor of the principal. This is an assumption that is typically made in Stackelberg case. But in our setting, we let the agent tie break however they like, including adversarially sort of against us. And so we have to handle that in our work. And what's our goal? Our goal is to minimize policy regret, right? So now I'm finally adding in this final element of the agent behavior, which is, again, we have this comparison of these two settings. Now, in our setting, in the actual utility that we get from our choice rule, we're thinking about what would happen in the worst case of over-agent behavior based on the constraints that we've given them. And then in the counterfactual benchmark, we let it be the best case over their behavior. And still, we have the adversary choose the state of nature sequence to maximize this step. Wonderful. I'm going to hand it over to Han.
Okay, so we're not the first one to start this kind of prior free games, and actually this has been started by Camera et al. In 2020. Yeah, actually the co-author Jason is here. So in Camera et al, they also have similar no swap regret and no secret information assumptions. But first, our work significantly improved the computational and the statistical efficiency. So in Camera et al, the policy regret and the running time bound scale exponentially with the cardinality of the state space, the number of possible states of the nature. But in our work, we improved this exponential dependency to a polynomial. And this is because they require full calibration for the forecast. But in our work, we only have the forecast calibrated conditional sum event polynomial number of events. I will talk about which events we want to calibrate on later. And second, in common law, they assume that, okay, so we have this no swap regret as a behavioral assumption, which means the agent can, so there could be multiple choices of taking actions for the agent. They can either take actions in the favor of the principal, or they can take actions that is against the principal. And maybe both can achieve similar level of utility for the agents. And but this may increase maybe just make very a lot of difference for the principal. And common law assume that the maximum principal utility that when the agents best responds in favor of the principal doesn't really increase the principal's utility a lot compared to that they just respond against the principal. Then there is no tie-breaking issue because when the agents either respond in favor of the principal or against the principal doesn't make a lot of difference for the principal. But we don't make such assumption in our work. Instead, we propose something called stable policy oracle, stable policy, so that to tackle with this problem. So what is the optimal stable policy oracle? Well, we say a policy is stable under a prior pi if the agent take any action other than best respond to this policy p and the prior pi would either decrease the agent's utility a lot or achieve a similar level of principal utility as they just best respond to this policy p and the prior pi. Since we have this behavioral assumption that they will run algorithm with no swap contextual regret, so they won't take action that is significantly worse than best respond for them. So, the agent actually will, if we just implement this stable policy, then the agent will lead to the principal's utility that is comparable to the one achieved by best response. And then we see a stable policy is optimal if this policy and the best response to this policy will lead to principal's utility comparable to any consistent policy where the agent just the best roughly approximately best respond in favor of the principal. So then what we do is given a forecast, then we just call this the optimal stable policy oracle and output a policy that is optimal stable under this forecasted pi t. And then we show that when the forecast by running this optimal stable policy oracle, when the forecasts are well calibrated, we can guarantee diminishing policy regret. So what do I mean by well calibrated? So first, event is we say the forecast. If the forecast, we define a set of events, and we say if the forecast has small bias conditional on this event, then we say they are well calibrated. And an event is a mapping from forecast to 0, 1. So actually, an event define a subsequence here, and then we say the forecast has small bias conditional on this event if on this subsequence the forecast has a small error. And then we say the forecasts are well calibrated in our theorem that is conditional on the following events. So first, the set of events is for any policy P and action A, if pi t makes our rule output a policy and recommendation equal to P and A, then this defines the event. So we just enumerate all P and A, then we have a set of events. And the second set of events, that is, if the forecast makes the best policy, assuming the agent will epsilon best respond in favor of the principal, and the corresponding response is P and A, this defines as another event. And we also enumerate for all P and A, and this give us a second set of events. And we have a third set of events, that is, if pi t makes the best response to policy P not is A for all policy P not and A. This gives us the third set of events. So if our forecast has small bias conditional on the union of these three sets of events, then we can guarantee a diminishing policy regret. And so there are a polynomial number of set of events. And to achieve small bias, this kind of forecast can be achieved by this prior work. Okay, so far I have talked about that. If we have stable policy oracle and if we have good forecast, then we can achieve diminishing policy regret. But I didn't say how to construct a stable policy oracle. So in this work, we show how to construct a stable policy oracle in linear contracts and one-dimensional Bayesian persuasion. So here I just want to talk a little bit about like the intuition for how to construct a stable policy oracle in linear contracts. So in contracts, it is a linear contract if the principal just pay a proportion of the reward to the agent, and this proportion is denoted by alpha. And then in linear contract, the utility, the agent utility is actually is linear in alpha. So here we just draw this plot that every line represents the utility of the agent if they take a specific action, and it's a function of the utility and alpha. And then further, we just choose the policy, the optimal policy, by assuming the agent will epsilon best respond in favor of the principal. So we could find a policy. But then this policy might not be stable because there could be more than one actions that are best response to this policy. Like here is A2 and A3. Then what do? We just increase alpha a little bit, by a very small amount. And then there could be just then A2 is no longer the best response, but A3 is. So we have solved this tie breaking issue, but it is possible that then there is another action that is also best response to this new policy. So we introduce another tie breaking issue. What we do is we just keep increasing this policy until there is no tie breaking issues. And in the end, we could find one stable policy that is only one action that is epsilon best response to this policy by not increasing too much. So we show this policy is stable and also kind of optimal. Yeah, that's it.